of time before the light comes on to say it's recording. Okay, so we're going to follow a similar format to what we did for the waves. So we're going to have a quick overview of where to find stuff. What I've also done for this one, because there's also more stuff available, is this website. Jessie, if you can just switch off your mic because the noise comes through. You're welcome to switch it off, switch it on if you want to say something. Great. So this No Brain Too Small is a really great site. So I will just click on here and it should hopefully take me through to this web page. And the link I've given on there, and I will put that in the chat very soon, takes you directly to this particular standard. So it's done by a teacher in Wanganui, and she keeps it fairly updated. So what's useful is she gives an overview, some survival sheets, and what she's also done is she's collated the exam papers, but in certain parts, so everything on electrostatics. So if you want to say focus on electrostatics because that's your weak area, then you can just download that PDF and just work through lots of electrostatic questions. And again, similarly for circuits, if you're struggling with circuits or the electromagnets, you know, the right-hand rule and all that sort of stuff. So that's really useful. And then there are some more from further past papers as well. So I really recommend that you do work through those for practice. Again, if you're my student, you're welcome to work through past papers in total and upload to the Dropbox in the 1033 A Dropbox. For the rest, if I'm not your teacher, then just ask your teacher if they don't mind going through, you know, marking a past paper for you. So that is really useful. And if I look at something like this, you can see what's up here. They have a summary sheet. So if you have a look here, so if you want to have like crib notes while you're trying to work out what you know while you're learning, they have got all about a page on static electricity. Then they, okay, 2 pages on static electricity. Then they've got a page on circuits. They give you, for instance, a few definitions. You'll have to go through it, or you might want to write your own definitions on here. It's always useful trying to write definitions based on the equations as well. And then they've got magnetism with the rules, you know, the right-hand rule and so on. So very useful. So that was the first thing. Oops, Daisy. Let me first take this and put this in the chat. This is the, where's the chat? This is the one for, is it coming through? Yep. Sorry for the being so big. That is where you can find all the past papers and the assessment and the standard, as well as the assessment schedules. And this one that I'm going to do now is the No Brain Too Small. So if you click on those and you bookmark them, then it's easy access to those 2 web pages. Now, let's look at the standard very quickly. Pretty much it's in those 3 sections. So you're going to have static electricity. There'll always be a question on static electricity. And you need to be able to explain in terms of positive and negative charges attracting and like charges repelling. The fact that you can get conductors and insulators and so on. The uniform and non-uniform charge distributions. If you've got electrical discharge in the air and friction causing a separation of charge, those sort of things. Then for the circuits, You can get simple series circuits, simple parallel circuits, and we'll look at that when we go through some questions. The 2017 paper that I picked only actually had series circuits and no parallel ones. So if you struggle with parallel, go through that no brain to small and look at some questions. But here are the four equations you are supposed to know. So this is to work out the total resistance of a series circuit. This is when you've got power related to time and energy, or power related to current and voltage. And this is voltage related to current and resistance. And then finally, you've got magnetism, and you need to use the right-hand rule to work out magnetic fields and so on. As well as being able to calculate the strength of the magnetic field. So B is the magnetic field strength in Tesla. K is the constant, which will be given, as I'll show you. I is the current, and D is the distance between 2 points on the electric field. Okay, now you are given all those equations, as well as you're always given the K, the constant that is in this formula. So any questions with that before I move on? You're welcome to put questions in the chat at any time. Now, again, it's really important that you know what these things stand for. So make sure you know that V is the voltage, and it's measured in volts. I is current, and it's measured in ampere, or capital A. Don't say amps. It's not a good look. Okay, I don't think at level 1 it's marked wrong, but it should be ampere, capital A. R is resistance, and it's measured in ohm. So here's again our I and our V we've done, and so P is power, and it's measured in watts. So make sure you know these. So when you read a question, if you are given something and there's a W after the number, you know that they're talking about power. Or if they give you a number with an A after it, that's the unit, you know that it's talking about current. So it's really important that you know these. And then similarly, here's P again for power, E is for energy, T is always time. Now time is in seconds. So if you are given hours or minutes, convert to seconds, really important. R, as we've seen, is all resistance, and it's measured in ohm. And then here again, this is the electric field strength, and it's measured in Tesla, and it'll be a capital T. The unit for K is given, Tesla meters per ampere. I is an ampere, and D is important to remember, it's in meters, okay? Because it has to cancel out properly when we use this unit. So if you're given centimeters or millimeters, make sure you convert to meters. That's often a trick thing that people don't do the conversion. So do you all know, hand over heart, all these formulae, the quantities and their units? So if I say P, you can say power measured in watts. And if I say D, you can say distance measured in meters. Do you all know them like that? Because if you don't, make flashcards and learn them. Right, carrying on. Let's now do, this is a 2017 paper. And as you can see, if you have a look and you see charges, this is going to be electrostatics. So basically what they're saying, spray painting. Now they'll give a picture. If you go to the NZQA site, you're not going to see this picture. The picture is not important. It's just sort of just to give the context. Okay, so you can still take a past paper from NZQA and do it even though the picture's not there. I've been able to get into the NZQA site and I can see the copyrighted stuff. Okay, so here we've now got a spray gun spraying paint, and so we know the paint droplets are going in this direction to the metal surface, and we know it's a metal surface, and we know that it's being charged in some way. You know, there's obviously connected with some sort of current here. Okay, so describe the key property of metals that make it suitable. So if you see negative charges or even positive charges, hopefully you will immediately think of, is it a conductor or is it not a conductor? Okay, so metal can be painted very easily this way because it is a conductor, which means charge can move it through it very easily. And hopefully that was okay for everybody. It's a straightforward achieve level question that the metal is a conductor. You could be specific of electricity just to differentiate it from a conductor of a heat, but so charges can move through it. It does say describe, it doesn't just say what, so you could perhaps say which allows charge to flow through it. Okay, now one reason for charging the droplets is to ensure that the paint is evenly spread. So they scaffold the answer by giving you in steps. So this is part 1. And they're saying what happens when I have got 2 negatively charged. So you can either show something like that, or you can have the arrows on that side. But basically, you want it to show that they are being repelled away from each other. You're not going to show them being attracted to each other. That's going to be wrong. And that is going to be right. So simple, straightforward repulsion. Now, because this is part 1, you know you're going to be using this in the next question or later on in the same question. And that we can see. Oh, is my screen share frozen? Is it just Quinn or anybody else? Okay, Quinn, it might be the heavy bandwidth. Yep, refresh your page. If you missed this little bit, then you can get the recording just to see that bit. Okay, now how does negatively charged, just a little bit glitchy, what I might quickly do is I'm just going to disconnect from something, and hopefully that will make it stronger on my end. Okay, right. So now how does negatively charging the droplets spread the paint evenly? Okay, yep, it could be because I was also connected to something else. So here now, go back and look at the question and see if you can get any clues. So we can see they're being distributed, you know, they're here, it's close together, there they're going further apart. So really what you have to do is just put this and state the obvious in words, where they are all negatively charged, so they're all going to be repelling each other. And because they're repelling each other, they're going to spread further apart and therefore will cover a bigger area. So nothing that I've said is difficult. If anything, people don't do well because they didn't say all that obvious stuff. So just have a look and try, as I say, explain to a 5-year-old or a 10-year-old, something, even real obvious stuff, spell it out. So the charges are negative. Like charges will repel each other, so the droplets will spread out and cover a bigger surface area, and therefore they'll also be more even, because if you do yep, correct, when that's nice and succinct and you've actually got all the bits there, that it covers a bigger area and it's even because the opposite charge repels. Yep, you've got that brilliantly. Carrying on. Okay, now this is explain. It can go up to excellence if you see this. There's not that much space given, so it could be a merit level question, or it could be excellence. Let's have a quick look. Actually, I'm just going to go. Okay, now. Right, this is rather on the small side. Yep, so it just goes to a merit level question, this particular one. Often, though, if you see the word explain, it can sometimes go to that top one. They actually did. Oh, no, we're over here, part two. Let's carry on with the other one. When spray painting metal objects, a power supply can be connected, and we know that this was put into metal. Well, here now we've added as a special one, which allows the back of the object to be painted. Now, what you need to see here is hopefully you will recognize that the long stroke is positive and the short stroke is negative. So the metal is, hopefully you can see, positively charged. That's the way this is going to be particularly working, and the circuit is completed by the spray paint landing on there, and that makes it connected. So this is a positively charged plate, and again now you have to just spell out the obvious detail. Because this is positive, it's going to attract the spray paint. So if the spray paint goes past it, it's positive on the back end as well as on the front end. So it will, any spray paint that goes past will also be attracted to the back of the metal. So just those rather obvious things, just put them down. Obviously, more paint is going to go more on the ends rather than the middle, but depending on how big it is, it could go all the way around. So that is just simply recognizing that this is a positive end. And the way I always remember is positive is like two lines. So if I connected the two lines together, it makes it longer. Okay, let me do another color. If I've got that one, that's that bit. And if I've got, this one, that's that bit. So it makes it a longer line. Whereas a negative is just one line, so it's shorter. That's the way I remember it, in case, if that helps. Okay, now we get to our a calculation, and we know it's a calculation because they tell you. Okay, they tell you what to calculate first. So you calculate P. That's why I say know what the quantity is and the symbol. Hopefully you can see that that is A, so we know that this is current, because current, which is a symbol of I, is measured in ampere. We know that that is J, and so we know it's joules, and we are also told that it's energy, and that is E. And we are told also this is kilovolt. Okay, so that is 1000 volts. And so this is 20,000 volts of voltage, which is V voltage, sorry. And we know from here that that is S, which is seconds. So we know this is time, and that is T. So we've got a lot going on here, but by identifying all those things, we've got current, we've got voltage, we've got energy, we've got time, and we are told specifically to start with calculating the power. So now we go, okay, I've got all that stuff. What do I do with it? So you just take this, and I'm just going to go Control C. Remember, go to your resource booklet and have it open. I'm just going to dump it in here. Okay. I'm going to make it really small. Where did it go? Over there. Right, so hopefully it is a bit on the small side, but these are the equations we are given. V is equal to IR. Now we're not given R, but we know V and we know I. We are told to start with this one. So we have to start with P. We do know I, because we're told it's there, and we do know V. Okay. We also get told to start with power, so we can use this one because we have got E and we have got T. So there's two different ways we can start this question, both calculating power, and both are accepted. We don't need to use this equation because, you know, we don't have a series circuit, and we don't need that at the moment because we're not calculating anything with a magnetic field strength. So hopefully you're all going to be choosing either P is equal to IV or P is equal to E over T, because in both of them we have to calculate P, and we are given the voltage and current, and we are given the energy and the time. So let's start. Let's just simply say P is equal to IV, which is equal to 1.0 times 10 to the minus 4 ampere. Notice how I write the formula first. I don't just make masses of numbers. Formula first. And then I substitute and I give my voltage. And notice I am putting in my units because I want to make sure I am using the proper units of volts and amperes and not things like kilovolts. And if you have that, you will get an answer of just 2. Now, please don't use just an answer of 2. You are given 2 figures over there and 2 figures over there. So you should say 2.0. And then what else do you need to do? If I've got my answer, what do I also need to add? I always need to the units, and in this case it's watts because it's power. Now I've done that, and now I've got to think, okay, all I've done is I've identified things, I've chosen a formula that I can use, and I've calculated it, but what does this actually mean? So if you think of the ones I've used, this is the maximum safe current. So what I've done is I haven't calculated whether this is the power that is actually in the spray gun. I have calculated the maximum power that can be used. to be used safely, okay, because that's a safe one. Now, they have asked us specifically to calculate the power drawn, the power drawn by the spray gun. Oh, why is it not going to there? So I want the power drawn by the spray gun. So I want to know, is it going to be more than 2 watts or is it going to be less than 2 watts? Because if it's less than 2 watts, then I'm fine. But if it's more than 2 watts, then it's not fine because then I'm going over the safety. I will be using more, the current is going to be higher. So what you now need to do is go, okay, let's look at the other option. Now I've deliberately, yes, so Quinn, you've gone straight to it. I've deliberately done it as though I didn't quite know what to do. And so I was just going to be looking at these things. So what the spray gun is actually doing is this bit over here, which means we now need to use that equation. Okay, so we now go, and I'll do this in a different color, of P is equal to E over T, because this is what it's actually drawing. It's drawing 3.8 joules over in 2 seconds, 2.0 seconds, and that makes it 1.9 volts. Thank you, Quinn, for giving me the answer there. I don't have to calculate it. Sorry, not 1.9 volts, watts. Okay. So because now that is the power that the spray gun is actually using, and it's less than the maximum amount, it is safe to use. It is within safe limits. I could then, if I wanted to, if I didn't do this, there are so many ways to answer this question, but this was the key one that you needed to have. I could have then worked out the current and seen if the current was going to be bigger or smaller than that. But any questions of how to approach these types of questions? If you don't know what you're doing, it doesn't matter as long as you know the quantities, the symbols, and the units. Because once you can identify what these quantities are, you just look up in the resource booklet for a equation you can use. So if they've got like 3 things in the equation and you know 2 of them, you can always work out the 3rd one. And then work it out and give an answer, and you will probably be getting an achieved point for that, even if you had no idea what you were doing. But here we did the first thing, then we looked very carefully to see what we were working out, and we could then get now the final excellence for this. Okay, so hopefully that is helpful. Here, question 2. We've got now half an hour left for the rest. Again, what I said in my waves one, the examiners do not like you to go, oh, I made a mistake, let me cross it all out and try again. If you made a mistake on your diagram, please go and use the identical one on page 10 and draw it properly there. And if you like, say, see page 10 so that they can give you the mark over there. So we've now got a simple circuit, and hopefully you can recognize that this is a series circuit. And we know it's a series circuit because the current only has one branch or one way to go through. It doesn't split anyway. So my charge, each coulomb of charge, it picks up 12 joules of energy, will go through both the thermistor and use up some energy there, and it'll use up the rest of the energy here before it gets back here to pick up more energy again. We just simply assume that the wires have so little resistance compared to the resistors and, you know, the bottom 2 that we can ignore any resistance there. So the first thing you need to do is to draw a voltmeter to measure the voltage across the thermistor, because that 12 volts over here is divided across this one and that one. The total voltage across both will be 12 volts. And hopefully you know that voltmeters are connected in parallel. So I have to make a connection on this side of this thermistor and on that side of the thermistor and connect my voltmeter in between. So it's measuring the difference in potential energy from this point to that point. Any questions so far? That is a very straightforward achieved point, and hopefully you would all get that. Now we have done that first bit. So we've drawn the symbol for a voltmeter and we've connected it, as I say, in parallel on either side of the thermistor. And now we have to do a calculation. And again, we can recognize a calculation because we've got a whole lot of numbers with units, so we need to do it. So it's the same sort of thing as what we did before. Now here, it is really important to show full working. You can't get anything unless you show full working. When you're told that you've got to show that the answer is this, you've got to show every single step. So don't just write a mass of numbers and make it equal to 860, because you're not going to get anything for that. You have to show all the steps. I'm going to just quickly take my, where did I have this? And I'm going to dump it over here. So always refer back to the, I'll just do it over here. Always refer back to the resource booklet. Don't try and remember in your head. So again, you've got to show what the total resistance is. So this is R. So we know, yep, you're way ahead. So we've got total resistance, and where do we find resistance? We find R over there. We know ampere, A is ampere, so we know this is current, which is measured in, or which is given the symbol I. So we know that one. And we are told, not in this question, but in the diagram, we are given the total voltage. Because remember, the battery supplies in a series circuit the total voltage for everything. So we know that V is equal to 12.0 volts. And yep, so correct there, Quinn. So basically we're saying, okay, I know V, I know I, and I therefore can calculate the ohm, which is this. So you would write the equation. V is equal to IR. Change this to what we're trying to find, the R. R is equal to V over I. I know I have to divide by I, because if I is multiplied by R, on the other side it has to do the opposite, which is divide. And then I substitute my values, which is 12.0 volts by 0.014 ampere. And so I get an answer 857.14. And of course, we don't want to quote an accuracy we don't have. So we're going to round it off to 2 significant figures, because all of these are just going to 2 significant figures. So it's 860 ohm. Any questions on that? That's a straightforward achieved, but if you missed out those steps, then you wouldn't get anything. So whenever you see the word show, it means they're giving you the answer, so they want you to show every single step the way you got there. Now here it's calculate, and here now they won't mark you down if you don't show every step, but it is nice to work it out. So again, you have to work out resistance, but instead of doing the total resistance, which is 860, You only want to do the resistance across here. So we know that the total resistance, R total, is equal to 860 ohm. And we also know from this formula that R total in a series circuit is the sum of all the resistances in the circuit. So the 860 ohm is equal to this R2 and this R1 resistance. So if I want to work out R1, then it's just R total subtract R2. So you could basically say R2 is equal to 180 ohm. Therefore, R1 is equal to R total, subtract R2, which is 860, subtract 180. And my brain isn't that good. I used to be able to do these all in my head, but years of using a calculator, I can't do it anymore. 680, great. Now 680, now please, whenever you, so there was 860 and there was 680, and I thought, oh, what have I done something wrong? Whenever you do a calculation, always ask yourself, how many figures do I write down? Like here, you didn't write down all the figures, you rounded them off. Do I have a unit? So make sure you write the unit, its resistance, and you go, is my answer sensible? And you go, yep, it looks sensible because the resistance for R1 must be less than R total, and 680 is less than 860, so it looks fine. Any questions so far? Right. Now here we've got, and I've just copied this one through, it's always nice to always refer back to the image, because then it's just easier to try and work out. Now we are told as the temperature decreases, the resistance increases, so R increases. We had worked out it was 680 ohm. Now it's going to go bigger than 680. So what will happen to the current if we now decrease? So again, it's when you have explain, this is probably going to be at least a merit, if not an excellence level question. And spell out the obvious, just state the obvious. It's also very useful to, and I would strongly recommend it, to always refer to one of these equations that you are given here. Okay, so the ones you need to talk about is obviously something with current and resistance in it. So I would choose this one. So we could start off by saying, because V is equal to IR and V stays at 12 volts. You could have said stays the same, but to show that you've understood the question, you can give specific detail to say, hey, I can apply my knowledge to this. So because V is equal to IR and V stays this, at 12 volts, therefore I is, or you could say current, if you could say I, it doesn't make it, therefore current is inversely proportional to what was it? A resistance. So we've given the science background, for want of a better word. Now we're going to apply it. So now we're going to say, so if temperature decreases and the resistance, sorry, excuse my spelling, of the thermistor increases. Okay, so that's the word. So because current is inversely proportional to resistance, and this is increasing, that means that the current must decrease. Therefore, the current must decrease. Okay, so if you just simply said, which most people would simply say, oh, resistance increases, therefore current decreases. You're not going to do that well. You have to show all your thinking steps. So if I now look at the assessment schedule for this particular one, if you just simply said, you know, it's the resistor voltage decreases or power decreases, that's just achieved. You've got to say more. So can you see here, for as the temperature decreases, the resistance of the thermistor increases? I'm really repeating a bit of the question there. Now, actually, they've given more detail than what I've done, because they've now said this increases the total resistance of the circuit, which I didn't really write. So that's an obvious statement. You know, I just assumed that people would know that, but write that down. And therefore, the total current will decrease because, and this is the important point that I did mention, the voltage stays constant. Okay, and they've actually also said here now, okay, this is actually, I think we've done C. We're busy with that one. That just simply goes over here. Sorry, yep. Thank you, Danielle. As I saw you type that, I thought, hey, yes, I will be sending out the recording, you know, just the link to the video as well. Okay, so I jumped the gun a bit. So that goes up to a merit level, but you did need to do the linking. And can you see it was linked over here? So if you have something there, then you will get something over here as well. Okay, right, let's go a little bit faster because time is going. That's my problem. I can often just talk too much. Right, so that was here, and perhaps the number of lines will give you an idea of how much to write. So explain how the power, so again, now you would use the formula, refer to the formula, where you've got here P is equal to IV, so refer to that. P is equal to IV, and make sure you refer to this, because if the total current decreases, then the total current going through the 180 ohm resistor will decrease as well, because it's the same current that goes through all the same thing. We know that voltage stays the same because it's 12 volts regardless. Okay, so if now, because power is directly proportional to current, if I decreases, then power will also decrease. So pretty much what I said for C, I'm going to be saying the same thing for D, but I'm just referring to a different equation. Any questions with that? So spell out all those little steps, and I can't emphasize enough is relate your explanation to a formula. V is equal to IR, P is equal to IV. Make sure you relate it to that. Even when you're asked to define something, it's helpful to link it to a formula. Right, let's now move down to the last question. Now here you do need your right-hand rule, and that, remember, is for conventional current. So when you have a look here, remember the long thing is positive and that is negative. So our current, our conventional current, yes, we know that. Oh, how do you know if something is proportional? If I've got like P is equal to IV, then I know that P is directly proportional to I, and P is also directly proportional to V. Okay, or because as P gets bigger, V gets bigger. If P gets bigger, I gets bigger, assuming that the other one stays the same. But if I now am comparing I and V, because they're next to each other, if P stays the same, if I gets bigger, V must get smaller to make P stay the same. Or if you were trying to rewrite this, and so you were trying to have I by itself, I is equal to P over V. So P is inversely proportional, assuming that, sorry, I is inversely proportional to V, assuming that power stays the same. That means the bigger I, the smaller V. So if you just simply use the equation, given the formula, if they're on the same side, they're inversely proportional, assuming the other one stays constant. If they're on opposite sides of the equation, and assuming the third thing stays constant, then they are directly proportional. As one gets bigger, the other one gets bigger. Does that help, Quinn? Hopefully that makes sense. Right, so going back to this, we've got now our current flowing around here. Now, if you have a careful, it's quite hard sometimes to see, so have a very careful look at the solenoid. Can you see that the current is flowing from the back to the front, round to the back to the front, and all the way coming here to the front and back down again? So if I was doing my right-hand rule, now I don't know what it's going to look like in the photo. Yeah, if I'm looking at the picture, I'm making the current do this, so my thumb points to the north, to the right. You're probably going to be seeing the reverse, unfortunately. But hopefully, if you all look at this picture and you use your right hand, if you make your fingers curl to the front, so if that's your thumb, and your fingers now curl to the front, then this is going to be the North Pole, because that points in the direction of north, and the current is moving forward in the curl of your fingers. So this is the North Pole, this is the South Pole over here. I'll just move because the thumb points in the direction of north, which is then on this end, because I'm going there. So that should be fairly straightforward. Now they do ask you to do the shape and the direction of the magnetic field. So I have done, and I've labeled you've got to label the north and the south. So you've got to have arrows and you've got to draw the magnetic field. So that means a whole lot of lines. So let me just sketch this out again. Keep your lines evenly spaced through here. Use a ruler if you can. I don't call this evenly spaced, but keep it evenly spaced there. And then it will go around and then it goes further out. So this is terrible drawing. I hope you get the idea that it's sort of even on this side or even in the middle, evenly spaced lines. Then these will be quite close to, well, it'll be as close as that. But when you're comparing it from outside, it'll be close here, and these are further, they get further and further apart the further away you go. So I've drawn it badly because I've made it close there and far over here. But try and make it close, and as you go, draw each line, make it go further away. And then do the same thing on this side. Let me see if I can do it better. So fairly close, and then the next one, make it go a bit further, and then this one even further away. So you want to show that the electric field is getting weaker as you go away. And then that's north and that's south. So if you look at a picture, nope, that wasn't the one I wanted. Over here. Okay. So here they haven't actually shown the things in the middle there. I suppose you can just ignore that. But can you see they're sort of close together? And as you go further out, make sure it goes further apart. And you've got to have labeled. So here for merit, you've got to have the correct direction. Now, I did not put arrows in my diagram, so I wouldn't even get, I would get achieved, but not any higher. Because you've got to have the arrows, the north and south, and showing that it goes further apart the further away you go. Right. Now that sounds really terrible, that drawing, but hopefully you get the idea. Now the resistance of the solenoid is negligible. Show that when the switch is closed, the current is now again. This is the special word show, which means please write out everything. So here we know, because it says A, this must be current. So this is I for the symbol. And what else are we given? We are given that it's 12 volts that's being supplied in total. And we've got also a resistance there. So what we just need to do is think of what we've given. I've got V is equal to IR. I know what this is, V, because it's 12 volts. I is what I've got to calculate, so I'm going to leave it as I, times. Now, because this is straightforward wire, we simply assume that the wire does not have the resistance, any resistance. I mean, in practice it does, but we just simply say, assuming relatively to the rest, it's not much. So our resistance here is the 28 ohm. So we've, whoops, we just calculate the 28 ohm. And so I is equal to 28 ohm divided by 12. And no, I've got something wrong there. Because I've gone wrong, I should have 0.43. Oops, what have I done wrong? I have done I have put those incorrectly, and you would have picked that up if I'd carried on, because if I said divided by 12 volts, it's ohms divided by volts, which I suppose you won't really pick up because you just simply would have put the answer as ampere. But because they gave you the answer, you go, oh, I did that wrong. It is 12 volts divided by 28 ohms. And that should be then the 0.4286, which is 0.43 ampere. I'm in a way glad I made a mistake, because by substituting too early, I went wrong. Perhaps say V is equal to IR, therefore I is equal to V over R, and then substitute the 12 volts by the 28 ohm. Oops, that's frozen on me. Oh, I'm frozen. Yep. Are you okay? Have we frozen? Or you can still see me and hear me? Yep. Okay. Unfortunately, my exam overview has decided to go on a total freeze. What I'm just going to do is I won't be able to put the answers in, but what I'm going to do is I will just look at the exam paper over here, and then we'll just look at the answers. Oops. So what have we got here? These are all the redrawings. Okay. Now you've got to do the calculation for a magnetic field. So whenever you see something like this and you get given a distance, now you have to use that equation of your B is equal to Ki over D. And the biggie over here is this is in centimeters. Do I measure distance in, oh, can't you see my screen? I will stop sharing and reshare my screen. Hopefully that is better. Okay. Yep. So I'm just using now the web thing from NZQA, because I can't now write, my other one is now stuffed. So here now you've got to calculate a magnetic field, and you're given a distance of centimeters. So you need to convert centimeters to meters. And this is where I find a lot of students go wrong, because they think, oh, it's easy enough to divide in my head. To go from centimeters to meters, I divide by 100. And I'm just going to move the decimal point. But a surprisingly number of students do that incorrectly. So always use your calculator to do that conversion, so you don't go wrong. And yep, so that's for that one. Otherwise, it's a straightforward calculation, just putting it in. And then here it's an explanation. And what you need to explain is, must the switch be closed or open to lock the door? And obviously the switch must be closed, because electricity must flow to get this to be magnetized. So you must tick off these bullet points as you answer them. So describe how doing this locks the door. So switching, it must be closed. The switch must be closed to let current to flow, to close the circuit. And this will magnetize this the solenoid and cause an electric field. And in particular, this core is going to be turned into a magnet, an electromagnet, with the north end on this side and the south end on that side. The material it is made out of has to be soft iron, because soft iron magnetizes really quickly, and the moment you switch it off, it demagnetizes just like that. So you want to have something that goes quickly on and quickly off, because if it doesn't lose its magnetism quickly, you won't, if you flick the switch to switch off the current, you're not going to be able to open the door because the magnet's still going to hold. So it's really important that you stress it has to be soft iron. And of course, the moment this gets magnetized, remember this is the south pole over here, and that's going to magnetize the metal as well. And anyway, you know, a magnet is attracted to a metal. So this door plate has to be metal to attract the magnetized soft iron over here. And again, you would like that to also be soft metal. So again, it can lose its magnetism straight away, because this metal will also be affected by the magnet. That's because you've created a magnetic field. Yeah, so the key thing is it has to be soft iron, so it gets magnetic very quickly and it loses its magnetism really quickly. So just make those statements very obvious statements. So that was it. Sorry, I've gone a bit over. Hopefully that has covered the major points. Please, as I say, go to no brain to small, because none of these questions here were actually a parallel circuit. And often the standard question is comparing series to parallel. That tends to be more often. I just picked 2017 just to be standard across all my lessons. But I do want you to go over that bit. Any questions on your end? I'll stop recording.